Good morning, good afternoon, and good evening. This is our third workshop of the year, and we want to thank you all for joining us and let you know that we greatly appreciate you taking time out of your busy day to join us. I'm Tom Concolino, and I'm here with our presenters, Aya Takase and Angela Criswell. Thank you all for attending Rigaku's virtual workshop, X-ray computed tomography for materials and life science. This session is on CT data analysis techniques using Dragonfly. And this session will be taking place in the lab with Angela and Aya reviewing in real time how to use Dragonfly to process scans on a variety of samples. Now, please note if you missed any of the previous workshops, you can view them on the Rigaku website. We also want to welcome Dr. Mike Marsh, the Dragonfly product manager from Object Research Systems, as a guest panelist. He'll be able to add additional thoughts and answer questions throughout the session as well. Before we start, a few housekeeping items. As far as today goes, this is going to be an interactive session like our previous sessions. We'll still be taking your questions live during the workshop, but we'll be answering them during the session, so please don't wait until the end to ask. And as usual, please submit those questions via the Q&A button at the bottom of your screen. Now, we won't be monitoring the raised hand function, and I will be posting relevant links in the chat window. Now, we'll be trying to answer as many questions as we can during the webinar, and we'll respond to any unanswered questions directly after the session is complete. If for whatever reason you have difficulty viewing the workshop live, please note that it is being recorded, and you'll be able to view the recording beginning tomorrow. Okay, and with that said, I'll turn it over to Angela, Aya, and Mike.
Well, thanks, Tom. Thanks, Angela. And thank you very much, Mike, for joining us. It's great to have you. And thank you everyone for attending the workshop. So today we're presenting live from our X-ray lab in the Woodlands, Texas, and we will be demonstrating X-ray CT data analysis using Dragonfly. So in this session, we will cover some basic steps of CT data analysis, and we will also talk about different image segmentation techniques, and we will talk a little bit about quantitative analysis as well. And the tool we are using today is Dragonfly 2021 from Object Research Systems. Okay, so let me switch the screen to Dragonfly and let's get started. Okay, let me make sure that, yeah, you have the view. So this is the interface of Dragonfly. And the main focus of this workshop is to learn how X-ray CT data analysis is done, not necessarily to learn how to use Dragonfly as a tool. So we'll focus on the analysis aspect of it. But if you want to learn how to use Dragonfly, actually Mike did a really good webinar series last year, and it's all available on the YouTube. So I would recommend you take a look at his webinar series. That's a really good tool you can use to learn how to use Dragonfly. I think, Tom, if you can put the link in the chat, that would be great.
Yeah, I just posted it, Aya.
Okay, thank you. All right, so we will take a look at a couple different scans today, but let's start with something simple. Now, I'm gonna load a scan, CT scan of a pecan nut, a pecan nut. But before we do this, so Angela, let's ask the audience what we need to know when you're loading a scan into analysis program.
All right, so I've just launched a poll where you can pick what you think we need to tell Dragonfly. Does it need to know the model of the CT scanner? Does it need to know the voxel size? Does it need to know the file format? Or maybe it needs to know the X-ray settings. So place your vote. We'll wait a few seconds and to let everybody get a chance to vote. And then we'll share the results with you.
It looks pretty good. Looks like everybody knows what they're doing.
Answers are coming in fast and furious.
They are coming in fast and furious. All right, 2 more seconds and then I'll end. All right, I'm going to end the polling and share it with everyone. So the item that received the most votes is the voxel size. So let's talk about that.
Okay, so this was a multiple choice question. You know, it doesn't need to be just the voxel size. And the second one I said it was a file format, and most of you got it right. So let's see what happens when we open the scan. So let me go to the file menu, and because we're opening a general scan file, I'm going to go to import image files and click add, And this is the pecan not scan. So I'm going to open this. And if the file has the correct file extension, in this case, a TIF, then Dragonfly wouldn't know what format it's in. But if you don't have the file extension or you have something weird as file extension, you probably want to know what file format it's in so that you can load it in the right way. And then once you open this and go to the next screen, you see a lot of parameters you can set here, but the important parameters are those three: X, Y, Z, image spacing, a voxel size, in other words. So you got this one right. You need to know what the voxel size is when you're loading a general scan. And for this one, it is 120 microns. So let me just type 120 in. And the fact that you can specify X, Y, Z voxel, size or dimensions separately means that the voxel does not need to be a cube, but usually it's cube shaped. Now, let me click this one so that we can take a look at the scan before we load it. So you can go through those slices to see what you're about to load. And you realize that the first 100 or maybe 150 slices really don't have anything meaningful in it. So in that case, let me go to 144. I can crop this data so that I don't need to open the first 144 slices. And I'm going to do the same thing for the inside. Yes, that's probably good enough. And I can do this in the XY direction as well. And the reason why I'm doing this is you can crop the data to make the file you're loading to memory small. And by doing so, you can keep a lot of space in the memory so that you can use that for calculation. And in this case, if you do not crop this image, the file is going to take 128 megabytes space. But after cropping this, you will see this number change. It's 26. That's quite a bit of difference. And you're saving a lot of space on memory. Okay, so I'm going to click finish and load the scan. There you go. So you have different cross sections and you can go wherever you want to look the inside of this pecan nut. And this is the 3D rendered view. And you can change the lighting, coloring. You can actually have a lot of fun with this, but let me just change a few things to make it look more like a actual sample. Okay. And with this 3D rendering, you can also crop the area you're looking at to see inside of the nut like this. Okay. So this is a scan. You just loaded it and you can look at the image at this point. Now, let's say that let's look at this one. You can change the gray level to make it a little easier to see, or you can select a certain area to automatically adjust the window leveling. And you realize that this shell has a little bit lighter color compared to everything else. And that's because the shell is on a higher density. And you might want to do a lot of different kinds of analysis with this, but let's say that we want to see how thick the shell is. To do that, the easiest way to do it is to just take a ruler and look at the thickness. This is about 644 microns. It's a little bit thicker here, and you can just take any measurements you want this way. This is one of the very simplest analysis you can do. Now I'm going to go back this view, and we don't need those rulers anymore. Now, let's say that you want to just highlight the shell and get rid of everything else so that you can further investigate this shell. And to do that, you will segment the shell. And the segmentation, which is essentially labeling of every single pixel or voxel in the image as a shell in this case. And the segmentation is the very first step you, in most cases, need to take if you're going to do any quantitative analysis. And to do that, I'm going to segment and define the range for gray level. So shell is very bright, so you can just select the bright area. And if you go too far you lose a shell. You can step back a little bit so that you can just select the shell. I think this looks reasonable. You have a little bit bits left inside, and we can clean that up later, so I'm not gonna worry about that. And gonna click add to new. This means we're gonna add those highlighted voxels to a new region of interest. And let me name this as just shell. Okay, and I'm gonna turn this off. So we just did this by looking at a one cross section. Let me make this a little bit brighter. But we are doing this in 3D. So all those shell volume on it's selected now. Now going back to this view, go to center. Now I'm going to turn this off, and we realize that there are some little green pixels inside, and we don't want those because they are not belonging to the shell. And to clean this up, you can simply go to the shell in this list and go to refine a region of interest, meaning we're going to do some cleanup of this region of interest. And I'm going to choose just keeping the largest volume and getting rid of the small islands. So now they're gone. So you just have the shell selected. Okay. So at this point, you separated the shell from the main scan. So you can see this in 3D. Now, let me turn this off. And you can just investigate the shell, and you can crop it the same way we did it before. Let me crop it a little bit more. Okay. Now you can just look at the shell without everything else in it. Okay. So this is a very quick overview of a couple of things you can do with a CT scan. Okay, so let's move on to a different scan. I'm going to click new. I don't need to save this. Okay. And go to import image files again. So the first scanner I just loaded was just single file that I had hundreds of slices in it. But in many cases, you might have a folder that has multiple slices in it. And in that case, you can go to open folder and select the folder that has the slices. And now you see individual slices here. And in the same manner, you need to note the voxel size. And this one is 78.4. And I know that there is not a lot of empty space in this scan, so I'm going to just go ahead and click finish. So this is a CT scan of a golf ball. It's very dark, so let me adjust this. And since it's a sphere-shaped sample, all cross sections look more or less the same. Let me change it so that it looks like a golf ball. Okay, so this is a CT scan of a golf ball, and let me do it this way. So we need to look at only one cross section. Okay, so when you look at this cross section, you can see the shell. That's the hard shell of the golf ball, and inside you have, I'm guessing this is something elastic at the core. Now, let's say that we want to analyze the thickness of the shell, but not just point by point, but we want to see the entire thickness distribution of the shell. Now, we're going to ask you a question. I mean, Angela is going to ask you a question. What would be a reasonable steps to take to do thickness distribution analysis for this? Oh, Angela, I think
to
you're
do
muted.
that. Yeah, I was. So would you first do some smoothing of the image, detect edges, and then do the thickness analysis? Or would you do a watershed object separation, segmentation, and then analyze? Or instead, would you recommend segmenting, refining the ROI, and then doing the thickness analysis? So I'll give you a couple of seconds to vote. See lots of votes coming in, and then I'll share the results with you. Looks like most of you know exactly what you're doing here. So I'm just going to end the polling in a couple of seconds and share those results with you. And the majority of you have voted for segmentation, followed by region of interest refinement, and ending with the thickness analysis.
Okay, so that's what we're going to do. So I guess, either you already knew how to do this or you were paying attention, because I said that the segmentation is the very first step you have to take no matter what you want to analyze. So we're going to do that first. So let's just take a look at this one cross section and go to segmentation, and I'm going to define the range. Now, I'm going to try to get rid of the air outside of the bowl first. That's probably good enough. Maybe a little bit higher. Okay. And next, I'm going to get rid of the lighter part. That's the internal elastic core. Okay. So I'm going to do my best to get rid of all those pieces inside, but there are a little bits left, but that's okay, because the second step we're going to take is the refinement of a region of interest. So I'm going to add this. Let's say I'm happy with this result. And again, name this shell and turn this off. Okay. If you just highlight what was just selected or segmented, then again, you see the shell, but you have a lot of bits inside. You can go to refine region of interest, and we'll do the same operation. I'm going to just keep the largest volume and getting rid of everything else. So that's pretty clean. Now let's zoom in a little bit to make sure that we selected the shell correctly. Then when you zoom in, you realize that there are a couple of holes inside of the shell. And this is not going to be good when you want to do thickness distribution analysis. So I'm going to clean this up or close the holes by literally clicking this close button. And this is a morphological operation. And by doing this one, you can close most of the small holes. I'm going to click this, and they're gone. So it's pretty clean segmentation we have. Okay, so those are the first steps, segmentation and the refinement of the region of interest. Now we are ready to do thickness distribution analysis. So I'm going to use this shell, segmented shell, then go to thickness mesh. We probably want to sample it a little bit to save time and also make it smooth. Okay, so this will take probably a minute. And take questions.
So while that's going, Aya, we've got a couple of questions come in here, and one has a follow-up. So let's start with that while we have a moment. So the first question from Catherine was, can the user set the mesh size or element size in Dragonfly to control the level of resolution of the contour mesh and thereby control the resulting final file size written by Dragonfly?
I'll let Mike take that question. He will answer that better.
Knew that was coming.
No problem. So Dragonfly, everything we've seen so far is working in the image domain with segmented regions of interest. You can create meshes, and I think that's actually what Aya just did, is create a mesh. And one of the things that Aya did on that last operation was she set a downsampling factor, and that downsampling factor did in fact influence the element size. But to the rest of the question, can you control the level of resolution? What you can do after you compute a mesh is that you can decimate the mesh. So if your tessellated surface mesh is millions of polyhedra and you need to have it smaller so it's more manageable, you could set a decimation to target it at a few 100,000 polyhedra or a few 100,000 triangles instead.
Okay, all right. So there's a follow-up question to that, and then we can continue on. So the follow-up question, Mike, is can Dragonfly output a file of nodes and elements for a finite element model, or is CAD format the best option?
Right, that's a good question. I suppose it depends on if you're doing surface finite element modeling or if you're doing more common volume or solid mesh finite element modeling. So Dragonfly doesn't work in that part of the mesh domain. That is, we make the tessellated surface mesh, but not the solid mesh. So your best bet, if that's your goal of solid volume modeling with finite element, is to go ahead and export in a standard surface mesh format like STL or PLY. There are about 5 other formats that can export. And then you can take that through a workflow in some other tool that optimizes your solid mesh that you would then be able to bring into finite element modeling.
All right. Okay. Thanks, Mike. I won't let you continue, and we can address some more questions in the next example.
Okay. So what you're seeing here is the surface mesh, just Mike was talking about, and it's color coded for the thickness of the shell. And zoom in a little bit. You see the legend at the bottom. So yellow indicates thicker part, and green, blue, purple, as you go different colors, you see thinner parts of the shell. And you can see it in 3D, and also you can see it in cross section. Now, when you look at this result for this particular golf ball, what you notice, I hope you do, is that the right side of the bowl is kind of yellow and the other side is kind of blue-green. And this means that the shell thickness is not uniform. Or in other words, the elastic core is sitting a little bit off-centered from the center of the shell. Probably not a good thing for a golf ball. But this is something you can quantitatively analyze. And if you want to see the thickness distribution in a histogram, you can do so too. And from this, you can calculate the maximum, minimum thickness, or mean value, for example. Okay, so that was the golf ball. Let's take a look at something else. The next scan I'm going to load is already in Dragonfly format. So that means that I don't need to specify the voxel size. That's already in the file header. Okay, this is a CT scan of a foam material, or a earplug, in other words. And dark gray area is air, and the lighter gray area is polymer. So it's two-phase system. Let's say that we want to do some quantitative analysis. For example, maybe we want to calculate the porosity. And to do that, again, we have to segment this image into air and polymer. Now, let me make this one bigger. So this is the typical cross-section of the scan. We want to segment into 2 phases. Now, the question Angela is going to ask you now is, what would be the best segmentation technique to use?
Okay, so for this poll, you've got 3 options. Would you use machine learning? Would you use manually thresholding? Or would you use Otsu binarization? So I'll give you a few seconds to vote for this. It's coming out pretty even. Lots of votes coming in pretty quickly, and the numbers are switching rapidly.
Like a very equally divided,
Yeah.
this one.
This
It
must be a
is.
hard question.
Uh-huh.
Should be interesting. Wait a couple more seconds for a few more votes to come in, and then we'll wrap it up. So I'll just end this, and I'll share the results. And you see it's pretty even for all. And however, machine learning and Otsu binarization both are leading the pack.
Okay, okay. This is interesting. I thought that this would have like a clear winner, but not really. That's good to know. We learned something. Okay, so what I'm going to do is let's start with the Otsu binarization. And then we can gradually change the way how we do it, and you will see the difference. Okay, so this is a cross section, and I'm going to go to segment again and define the range. And simply, you can click upper Otsu to apply Otsu binarization and select the lighter part. And for the people that are not familiar with what an Otsu binarization is, it's just an algorithm that will pick the borderline between dark phase and light phase. There are many different ways to do this, and Otsu is one of the binarization algorithms. So by doing an Otsu binarization, you can select the most of the polymer, but you realize that there are a lot of red bits inside of air part, and that's not great. We don't want to have this. So at this point, you can try manual segmentation, meaning that you will change this threshold to see if you can clean this up. I'm going to try to get rid of the red pieces in the air section. by doing this. I'm going towards the right. Now, this is clean. Now, the problem is we have a lot of holes inside of the polymer face. So that's not good. But if I try to fill those holes, then you're going to select the air pixels. So what this means is no matter how you set the threshold, thresholding is not going to work for this scan very well. So we're going to try machine learning. When you use machine learning to segment an image like this one, what you're going to do is to show the machine how you would segment this image as an example. And the machine is going to learn how you're doing it and will do the rest of it. And that means we have to show an example. So let's do that first. And to do that, I have to create region of interest. I got polymer. I actually want to change this color to have a good contrast. Okay. And I will make another one for air. Like a bright colors. There you go. We got those two phases. And I'm going to select the polymer. And let me turn this off for now. And pick up a brush and essentially paint the polymer. What I think is the polymer. The thing about a scan like this, it's a little bit noisy, and that's why thresholding is not working. But when we look at it, it's really easy to tell what's polymer and what's air. So I can paint it like this. And it's important to get the borderline between those two faces right, but it's hard to kind of paint it clean. So I'm going to use this upper Otsu segmentation as my filter. Now, I hope you can see this, but this brush is painting only the selected red pixels. So this makes it easier to get the borderline right. And if you have some mishaps like those, that's okay. I can delete them and clean it up. So this is my way of showing an example to the machine. And I'm going to do the same thing for air. Now I pick up blue paint and I paint the air pixels. And the beauty of this is that you don't need to paint the entire thing. That would be a lot of work. But you just paint a couple patches as an example for the machine to look at and use as an example. I think that that's probably good enough. Okay. Now I'm going to combine those, just put them in one multi-row folder. And we're going to use this to train machine learning. I'm going to machine learning segmentation and make a new model. And let's name this as foam. And the model you're training here can be reused when you have a very similar looking scan. So you don't need to do this every single time. And the input in this case is the raw data, this gray level image, and output will be either polymer or air. Those labels will be the output. Method-wise, I'm going to just use random forest. And then we select data features. Those are the features for the machine to look at when it makes the judgment in terms of this is polymer or this is air. I'm going to add self-intensity. This is a original data itself. This is something you should be always using as feature. And let me just add two more things and I will explain what I'm doing here. So I just added the morphological and median. And then when I add, for example, median as one of the features to look at, what we're doing is, let's go to preview. You're showing this heavily smoothed image to the machine as well as the original image. And by looking at both of them, machine will do a good job to ignore the noise. So you can combine multiple features or different ways of looking at this image to help the machine to learn how to segment this image cleanly. Okay, so we are ready to start the training. So let me click this. And it'll be quick, but I think we probably have some time to take some questions.
All right. So we got a question from James. This is actually a follow-up to Catherine's. So he said, thank you for answering the mesh resolution question. And we may not be able to show it here, but where is the decimate option to decrease the resolution? So it may be that we have to address that after with one of the data sets you already did if it doesn't show up here.
Is it easier to show, Mike, if I had a thickness mesh or something in the view?
That's right, Aya. If you right click on the mesh in your properties and settings, then you'll see a menu of mesh options, and one of them is to decimate the mesh, and that'll pull up the
Okay.
dialog. You can key in the parameters for your mesh decimation.
Okay. When we will have another one of those mesh, as a result in the process in the workshop today. So
yeah.
when we have that, we can take a look at that.
Okay. All right. And actually, it looks like we're done. So why don't we do that, and then we can address a couple other questions
Okay.
as we continue through.
Okay. So this is the result of the first training. And you can see that this is a lot cleaner segmentation compared to what we're looking at with thresholding. There are some little pieces of pink left, but you can refine the training more, or you can just, call it a day and do this segmentation and clean up those little pieces later. Now, this is just one cross section. If you want to see how this trained machine will perform on the different scan, you can just go to a different slice. You can go to different slice and just click preview to see how it does. Okay, so not bad. Okay. Once you get to the point that you're happy with what the machine is doing, you can click segment to segment the entire volume. That will take a little bit longer. So I'm going to skip that process and load the one that's already segmented with other additional analysis results. Do this. I should do. Okay. So this is the 3D segmentation results. Now you can see that everything is divided into two phases. You can see that in 3D as well. And after you separate the phases into two pieces, let me turn this off. You can just look at one phase at a time. Let me add a little bit shadowing so that you can see it. There you go. So you're just looking at the pores in this case, or you can just look at the polymer part of it. Now, after this segmentation, you can look at this air phase again and take this out as an individual ROI. Then look at the statistics of this phase. Go this one. And for example, you can see the porosity as 82% for this sample. Or you might be interested in looking at the individual pores and their volumes, diameters, or aspect ratios, and you can do so by separating those objects into multiple phases this way. We're not going to go into the details of how we separate those, but this is one of the things you can do. Now, let's take a look at this guy. So this is the polymer thickness mesh. And you can see that mostly the polymers are very, very thin, but when those pores are connecting to another pore, you can see green and yellow indicating that the polymer is a little bit thicker. Now, Mike, would this be a good example? We can try right-clicking on this. Okay, let me try this.
Yeah. You'll see mesh decimator about.
Oh, there it is.
Yeah, right. Yeah,
You can see those parameters.
There are a couple of different algorithms and then a target reduction rate. So the mesh you're looking at here is 3.1 million triangles, and you could tell it to try and get that down to 300,000 or to some number depending on what your target of a manageable mesh might be.
I see. See, I learned something today too.
Exactly.
Okay. And go back to this. So we did a couple different things for this foam material. Now, let's move on to our last scan of this workshop today. This one is going to be a little bit different. I mean, the analysis we're going to do is a little bit different. So this is a CT scan of a wood frame. It's all dark. Well, let me adjust this. There you go. This looks a little bit better. Let me color this too. So this is just like a wood frame of the picture frame, or to be honest, this is something I found in a dumpster at work. And I think it's a, it's a piece of furniture coming from somebody's office. But nonetheless, I thought it was an interesting sample to scan. Okay, so let me get those lines. This is a cross section of the wood frame. And if you go to the surface area, it's pretty thick or dense. This blue line is represented in this right bottom view. So you can see that there are a lot of wood fibers. This is very well packed or high packing density. But if I go to the center area, you see a lot lower packing density. And it goes higher again when you go to this side. And then when you see something like this, one of the analysis you might want to do or might find interesting to do is to see the change of packing density across this line. So let's say that that's what we want to do. And again, we're going to ask you how we should do it. Let's do it, Angela.
All right, so I've launched a poll here so you can vote on how you might recommend approaching this. Would you separate the volume into multiple thin volumes, or would you run a slice analysis on the wood segment, or would you draw a line through and look at the profile of that line? Which one would you do? We'll give you a few seconds to answer. It's fairly even, but there's one eking out in front. So maybe a couple more seconds. And then I'll end the poll and share the results. So in this case, the most popular choice was to run slice analysis on the wood segment.
Okay. I'm gonna say that makes sense. So let's do that. So slice analysis is for people who might have selected the other two choices or not familiar with this technique, is to take one slice and calculate certain property on that slice, and you do that for multiple slices. So in this case, we want to, let's say, calculate the packing density of this slice we're looking at the right bottom corner, and do that for different slices one by one. Now, before I start doing this, one of the things I want to do is when you look at this blue line, this is a slice we're looking at the right bottom corner. It's not quite parallel to the surface. So let me just straighten this out so that it's parallel to the surface first. And I'm going to do the same thing here because I'm a stickler. I guess that's good enough. Okay. Now to calculate the packing density, you have to kind of specify what's solid and what's air. So we'll do segmentation. So for this one, I'm going to keep it simple and do upper O2 and see how this does. It's probably a little bit less like under selecting. So let me adjust it a little bit. That's probably reasonable. And we're going to just calculate the total of those wood selected pixels. So I'm not going to care too much about the little pieces or details and just name this as wood. Okay. Now we're ready to do slice analysis, which you can do by going to right click and start slice analysis. And now let's do region of interest area. Okay. And calculate the results. So what it's doing is calculating the packing density for this slice and do the same thing for all those 725 slices.
All right, Aya, we've had a number of good questions come in. I'm going to hold off on a few of them until the end, but I wanted to ask a couple here. One from Don says, "Is there ever a good reason to use anything other than machine learning for segmentation? Is it just a time consideration, or is it some other reason?"
Okay. I'll make a few comments, and I want to see what Mike, has to say about this question too. But so not many good reasons not to use machine learning. But one of them is machine learning is not perfect. You will see sometimes cases where even machine learning cannot do segmentation very well. And that's when I would switch to deep learning, which can do a lot more sophisticated segmentation. So that's one. The other one is, if you were to do metrology or very accurate dimensional analysis, then in many cases, your way of determining where the surface is and do calculation for the dimensions or maybe even comparison to CAD drawing, your process needs to be traceable, especially when it's related to quality control and pass and fail testing. Then using machine learning might make it a little bit difficult to make the process transparent and traceable. And in that case, you might prefer, it might be better to use more analytical technique, which you can understand and control better. What do you think, Mike?
No, I agree mostly with that. I mean, there are cases where for material scientists, you're often looking at very demanding samples that have subtle texture differences, where you strongly benefit from machine learning techniques such as the one we see here, or deep learning techniques. But in cases where you're using the CT system to image a simple system that might be a plastic part with an air background or a metallic part with an air background, in the case where you have simple high contrast phases, then you don't have to resort to machine learning, and you just can go with a simple automatic thresholding. But any case of the material samples where you have subtle textures, then I go directly to these AI methods.
All right, let's we got a couple of related questions, and then we can finish the slice. So if we'll wrap up on this machine learning. How do you know that machine learning worked correctly for the entire volume? So the comparison between a 100% desired detection to real detection. Can you influence, I guess, both positively or negatively, the AI detection by changing any specific parameters? So this is kind of a deeper machine learning question here.
In terms of fine tuning the parameters of how the network behaves, or choosing a specific algorithm to use to train, I will refer to Mike. But other than that part, you do have a control over how you train it, how your example looks. So if your example is sloppy, your machine learning segmentation result is going to be sloppy. So you have a control there. And also fine tuning you can do. In terms of how do we know if it's correct or not, ultimately, we're the judge of what's correct and what's not when it comes to image analysis. So if you agree with the result you're getting from machine learning, I would say that is correct. But if you look at the results and go, no, that's not how I would do it, or you're picking the wrong areas, then that is not correct. You have to change your parameters or training data.
I would just add to that when you use the deep learning tool, I don't think we'll see that today, but when you use the deep learning tool in Dragonfly, you can specify data for validation and data for test. And what that means is you can decide what is your accuracy requirement. Do you require 99% of the pixels to be accurately labeled, or do you have a lower tolerance? And then you can keep training or keep iterating until the algorithm succeeds on your validation data. So it's always important to make sure that you're validating not against the data that it's being trained on, so that it's not overfit, But happy to tackle that in a longer discussion. But the way Dragonfly is built, almost all of those parameters are open and transparent and extensible. So you can see exactly what it's doing and then decide whether it's going to be reliable enough for you, or if you need to keep at it.
Okay, all right. Let's see, I think the next questions we'll address those after we wrap up here.
Okay,
So,
okay.
all right.
All right. So we just did the slice analysis, and let's click this one. I thought I just did. I guess I didn't check this one. Sorry about that. 29 seconds.
No. All right, so here we'll do a couple of quick questions while this is ticking through. What happens if you input the incorrect voxel size when you're opening up like that TIFF image?
That's a good question. If you put something grossly wrong, you probably will realize that you did something wrong, because that voxel size is used to calculate everything about the thickness or pore size, particle size, on all those things. So if the correct voxel size is less than 100 microns and by mistake you put 1000, and you will realize that you did something wrong. But the tricky one is you put something slightly wrong, you might not notice it. So it's important to double check that you know the correct voxel size and type that in when you load the data. Okay. So let me separate this so that we can get a better view. So this is the slice analysis, which you can see as the packing density variance. So when I move this line, you will see this line, the blue line, move. So towards the surface, you see very high packing density. And when you come to the middle, you see lower number. And you can also see this slice changing corresponding to where this line is. So this is a very convenient way to see one parameter changing across one particular axis. Okay, so let me just show you a couple more slides and we're gonna wrap up and answer more questions. Let me go back to this. So before we summarize what we just learned, I just wanted to show you a list of things we did not cover. So we did not go into the details of object separation and deep learning. Mike mentioned deep learning a couple of times, and I just wanted to show you what those are because we want to ask you a question about them later. So object separation is a process to separate, in this example, for example, this is a sandstone CT scan, and you see the sand grains. When you just do segmentation, you're just labeling those pixels or voxels as sand. Then when you do object separation, you're gonna separate individual sand grains. Then you will index them so that you can analyze the grain size. Then you see the histogram of the grain size, it's color coded, and you can see most of them are pretty small, but you can easily identify green or red grains that are large. So to do this type of analysis, you have to do object separation after the simple segmentation. And then once you do this, you can analyze either the size of the grains or maybe orientation of the fibers or aspect ratio of fibers. Anything you can quantitatively measure on each object you can analyze. So that's object separation. The other topic we didn't cover much is deep learning. Now, I just wanted to quickly show you what deep learning can do in terms of segmentation. So this is a CT scan cross-section of a tiny particle inside of an orally disintegrating tablet. And this tiny particle has multiple coatings. Let's say we want to segment those coatings to do some quantitative analysis. And if you use just simple thresholding, this is the best you can get. So first of all, it's kind of noisy. You see those purple bits, it's coming from the noise. And also you cannot distinguish this core face and the outside layer because their gray levels are almost the same. So this is the best you can do, and this is probably not good enough. You can use machine learning, and this is what you're going to get with machine learning. This is a lot cleaner. You don't have a lot of bits coming from the noise, and you can kind of tell that this outer layer is a different phase, but you still cannot distinguish this core and outside coating because even machine learning is basically based on the gray level of local area. Now, if you use deep learning can take, for example, the shape, size, or location of a certain phase into consideration. And that makes deep learning a lot more capable in a sophisticated segmentation technique. And by using deep learning, you look at the same data and you can segment it this way. Let's zoom in a little bit. So you would have no problem distinguishing this core face and outside layer, and even this really thin light gray skin can be segmented as an individual layer. So you can see that the deep learning is a very, very powerful segmentation technique. Now, having covered 2 topics we didn't really cover, Angela has the last question for the audience.
All right, so we'll launch the last poll question. And in this question, we'd like to know which CT data analysis technique would you like us to cover in the next Dragonfly episode that'll take place later this year. So object separation, deep learning, additional quantitative analyses that we can do or other, and in that case, perhaps be more specific in the chat for this case. So I'll just leave this here for a couple of seconds, and whoever wins, and that's what we'll cover for the next
and the next
webinar.
Dragonfly episode is going to be in September, right?
Mm-hmm.
Yeah,
Correct.
so we'll
Yeah.
cover what you want us to cover in September. And while we're letting you think about it, one of our webinar and a workshop regular members on Joe Neely from AbbVie, he suggested that maybe we should monitor who's getting those questions right and give some hours at the end. And we thought that's a really good idea, so we're going to do that. So we will be checking who's getting those questions right. This one is not counted because there is no right answer for this, but for the ones we do have right answers, we'll take a look at who's getting those questions right throughout the season, all the way to, I guess we go to September.
Mm-hmm.
And we will announce the winner or winners when we do the viewer's choice episode in October. So keep up the good work, and I guess we'll check how many winners we're gonna have and what the budget is, and decide on what the award is gonna be.
Sounds good. All right, ready for the results. Let's share them. So looks like the majority of you, 64%, would like to learn about deep learning segmentation. And then behind that, quantitative analysis and their object separation. So we do lots of webinars. And so we'll be visiting all of these to see how we can incorporate them in some shape or form, even if they don't end up in the September webinar.
Yeah, we can cover them in separate episodes as necessary. Okay. Now we're gonna really wrap this up and answer more questions. So things we did cover today include some basic steps for CT data analysis. Segmentation first, always. And we looked at a couple of different segmentation techniques and a little bit of a quantitative analysis. Maybe we will do more in the future episodes. Now, I think we have probably a few more minutes to answer more questions.
We do have time for a pretty brief Q&A today. So here's a few questions that came in. One of them, and actually a couple of them, are related to this object separation. One is, can you export object separation and slice analysis data into an Excel spreadsheet? This came in anonymous. I'm not sure who to ask if they can elaborate, but maybe you guys have an idea of why they would want that information in a spreadsheet.
And the short answer is yes, you can. For, let's say, the object separation, you did volume analysis for different grains of pores, and you can export the list of grain size, for example. And I can see that, you might want to calculate, the average, some statistics analysis. You might want to make different graphs. You can do all those things after exporting the Excel file.
Okay. Here's another related question on object separation. Is it possible to differentiate between voids and materials as it relates to their specific shapes? So for instance, if you have spherical versus cylindrical voids, can you get specific volume of the void types? So I guess it would be kind of a separation of the different voids shapes and, right? So it's a multiple.
You can do that by, let's say you segment the voids first, then you separate those voids as individual voids. Then you can label all of them with their aspect ratio to categorize all voids into cylindrical ones and sphere ones. Then look at their volumes separately.
May I add something? So all of that I just described is available in Dragonfly today. Something we're doing right now, I think was done last week in the lab, was add new measurement codes for the objects that you're measuring, such as spherical harmonics coefficients that would give you a high level of degree of characterization of your particles, whether they're voids or grains or anything else. And something that we've been experimenting with for a while now, and we'd love anybody who wants to work with us or test this, is if you have a population of voids and you say, well, I'm not sure if these are different because they're elongated or they have some other attribute, but if you want to select a dozen of these voids and select a dozen of another population, and then ask the software, what's different about these, and go find the rest of these populations. So what we've seen today has been a lot about segmentation and machine learning on how to label pixels. But now what I'm talking about is machine learning and classification of measured particles. If you have any interest in that, then Aya can connect you to me, or you can reach out to me directly. But those are some things that are coming down the pike.
So I guess that's kind of unattended use of artificial intelligence, right? You don't know what you're looking for, but the machine can tell you what's different among those.
These are different.
No, we need more than that.
Yeah.
That's interesting.
Okay, a couple more questions, and I think we're going to actually run out of time, unfortunately. So this one goes back to the polymer examples. Is always thought that air pores were supposed to be very dark gray or black, right? And that doesn't appear to be the case in terms of what we were looking at with our polymers. And I think that might just be because of the contrast setting that we had.
That's just because of the window leveling setting. I can make them as dark as I want.
Okay.
Yeah.
Okay. All right. And then Mike wants to answer Alexander's question, it appears. So is there a quick and easy way to remove the background? So if you're just looking at pores, the background is not included in the thresholding.
Right. So it depends on your sample. There could be different particulars in how to answer your question. But if you have a sample that has internal pores that you want to characterize, and then there's also surrounding air, and you want to measure just the pores on the inside, but not the air on the outside. If your pores are closed off and they don't connect to the surface, then it's a simple problem. You segment all the pores, and then the tool Aya used earlier to extract the largest, when she did refine region of interest, process islands, give me the largest object, you would instead remove the largest object, because that would remove the big air bubble from the outside. You'd be left only with the bubbles you care about. If, however, your internal pores actually connect to the surface, then you need to do a trick to close off the pores. And we have a tool that's basically like shrink wrapping your sample. And it's also in the refined region of interest tools. And you can email Aya and she can connect you to me, or I can tell you more. But yeah, there are ways of definitely separating off the internal pores from the outside pores or from the surrounding air, if that's what you need to do.
Okay, all right. I'm going to try and get one more question, but it might be that you have to answer this one offline, because I'm not sure we have time to show it. So it's John asked if we could show an example of how to export the STL file format from Dragonfly. So my question, actually, this would be a quick one to Mike. Do you have an example of this in your webinars on your YouTube videos?
I don't know, there's too many hours of content to remember.
Okay, okay, all
Yeah,
right.
but
They're
it's
like a
just
40 episodes.
you just right click on the surface mesh and then say export to file, and then it'll let you choose.
Yeah, I
from
think it's
STL
on
to
the
file.
right click menu.
Yeah. so it's
Okay,
there.
okay.
And it's
All
in the
right.
help menu too.
Okay, good, good, good. All right. So unfortunately, we did have a few more questions come in real late here, but we're kind of running out of time. So rest assured that we do have those questions are saved. Aya, Angela, or Mike, if necessary, will be responding directly to these last few that came in. All right. Now, as I said, again, a recording of the workshop is going to be available tomorrow. An email will go out to all the registrants with instructions on how to view that presentation, and links to the resources mentioned today will also be shared on the landing page. In addition, in the chat, I'm putting in a quick reference guide and link to, sorry, my mouse died, quick links to sign up for our next session in June. We will be hosting another interactive workshop focusing on data analysis using ImageJ. I know Mike just muted us for that. On Wednesday, June 16th at 2 p.m. Eastern, 11 Pacific. So we look forward to seeing all of you then. All right. Thank you for joining us, and we will see you again in June. Have a great day.
Bye.